Yeah, I am Shaladi Blessing, my name, popularly known as NAJAMACADEMY. Welcome to another class on isomerism. Now, what's isomerism? Don't forget, I've given you an hint on this in our previous video. But when defining isomerism is just a phenomenon whereby we have compounds that have the same molecular formula but different structural formula. Now don't forget, when we are talking about organic formula, before we proceed to isomerism, the organic formula is divided into what? Into three. We have the molecular formula, we have the empirical formula, and we have the structural formula. Now don't forget the definition of the molecular formula. The molecular formula is the actual formula for what? For a compound. And the empirical formula is the simplest form at which each atom of this compound can exist. But the structural formula, in organic compounds, we'll mostly use the structural formula because the organic compound is mostly represented with the structure. Now, let us go to the isomerism. So, we have a principle whereby compounds have the same molecular formula but different structural formula. Then we call it isomerism. Now, the compounds that undergo this isomerism are called isomers. So, if we can say that a particular compound is isomer of another compound, now let us see, what are we talking about? Now, we have types of isomerism. The first one, we have the structural isomerism. We have structural isomerism. Number two, we have the stereoisomerism. Stereoisomerism. We have the functional group isomerism. We have the positional isomerism. Don't forget, this stereoisomerism is divided into two. That is, it is divided into the geometrical isomerism and optical isomerism. Now, let us look at this isomerism. Let me add one to it, making 5. These are the 5 I'm going to explain today, in which we have what we know as chain isomerism. Now, what is structural isomerism? What is stereoisomerism? And what is the functional group isomerism? What is the positional isomerism? What is chain isomerism? Now, follow me. The first one, the structural isomerism. If you are talking about the structural isomerism is defined. If you say the structural isomerism is defined as the phenomenon whereby compounds have the same molecular formula but different structural pattern. They have the same structure, the molecular formula, but different structural pattern. What do we mean? Now, let us see. For instance, if you have something like C4H10, this one is the molecular formula for butane. This is molecular formula for butane. Then let us see some formulas you can add here. You can have something like this: hydrogen, 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 hydrogen. Now when you check this very well, this is called butane. This is called butane. We'll call it N-butane, that is normal butane. Then this same structure, I can have it to be, you can have, I can have it to be this. Or better still, let me have it to be this. Bring in one here. Now, if you bring one carbon here, then this will come. And we check this very well. If you want to name this, you have this should be 2-methyl propane. We check this very well. This should be 2-methyl propane. because the longest carbon to carbon chain is this, according to the organic nomenclature I gave to you. And there is a material which is a ligand, which is found at the what? At the second carbon. So it is found at the second carbon, and that is why this methyl has the position of what? Of 2. That's why we name this compound to be 2-methyl, then what? Then propane. 2-methyl-propane. 2-methyl-propane. Now, if you check this very well, this is an alkane family. Alkane family compound. Then we can still have another one. Another one can be like this. The same structure. The same structure. Have it like this. Under this. If you check it very well, don't forget that each carbon must be tetrahedral. That is, it must have 4 bonds. The carbon must have 4 bonds. If you count this very well, this one is 1, 2, 3, 4. 4 carbon. And the hydrogen is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C4, 8, 10. If you count this carbon is what? 1, 2, 3, 4. And the hydrogen is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The same thing. If you count this one is 1, 2, 3, 4. And the hydrogen is 1, 2, 3, 4, 5, 6, 7, 8. We have one. Don't forget, each carbon must be tetrahedral. That is 1, 2, 3, 4. 1, 2, 3, 4. We have this to be, okay, this should not be part of it, because don't forget that this one is under the cyclo. This one is under the cyclo. Now, this should not be part of it. You can see that it's even good whereby we make that. If you count it very well, that's the carbon is 4, but the hydrogen is not the same thing with this, so it's not part of it. Now that means this C4H10 has 2 isomers. It has 2 isomers. But let me give you a shortcut formula to not waste your time, because if you are doing CBT questions, you may not be able to participate in drawing the structure like this. So whenever you are given an alkane family from number 1 to from the homologous series of 1 to maybe 8 or 10, you have the formula to say, we have the general formula for the alkane to be 2 raised to the power of n minus 4. 2 raised to the power of n minus 4. Then if you have 2 raised to the power n minus 4, altogether 2 raised to the power n minus 4 plus 1. 2 raised to the power n minus 4 plus 1. Now let us see, what is our n? N is the number of carbon in the given structure. Then, for instance here, if I'm using this formula to find the number of isomers for this, this formula is only work for the structural isomers of alkane. Then I will now say this is 2 raised to the power, what's the n value here? That is 4. So I have it to be 2 raised to the power 4 minus 4 plus 1. Don't forget that 4 minus 4 is equal to 0. 2 raised to the power 0 is what? 1. Plus 1, that's equal to what? 2. That makes this alkane family, the butane, to have 2 isomers. So therefore, if you are given something like this, let me say C6H, don't forget alkane is CN, H2N plus 2. That's 6 times 2, that's what? 12. Plus 2, that's what? 14. So if you add this, if they now ask you to find the number of isomers for this, then this would be 2 raised to the power, what's n here? That's 6. Minus 4 plus 1. Then this is 6 minus 4 is 2. 2 raised to the power 2 is what? 4. Plus 1 here, that's equal to what? 5. That shows that this has the number of isomers to be equal to what? 5. Someone will ask me, is this only peculiar to alkane family? No. We still have for the alkane. So, because of our time, I will not be able to go deep into the alkane family, but let me give you one structure for the alkane. Now, if you are talking about the alkane family, for the alkane family, if you are given a structure like C4H8, this one is butane, normally. But a particular molecular formula can be broken down into different structures. Those are the isomers. Firstly, if you have something like this, each carbon must be tetrahedral, that is 4 bonds. 1, 2, 3, 4. This one is also 1, 2, 3, 4. Then if you want to name this one is butane. This one is butane. Then at the same time, if you have this to be butane, then we can still see another structure. Let's see here. Let's say you have 1, 2, 3, 4. What if we take this double bond to the middle? We take it to the middle, you have it to be this. You have it to be this. 1, 2, 3, 4, 1, 2, 3, 4. Don't forget, this one will now be boots 2in. Boots 2in. The reason why it is boots 2in is because the position of the double bond is placed at the what? As the center. That is at the second carbon. Someone will ask me, what if we place it here? If you place it here, it's still booting in. It's still booting. If you place it here, it's still booting. Because you are going to start your counting from here. If you go through the organic nomenclature in our last episode. So this one will be what? Will be booting. If you still place it here, it will still be what? Booting. So we have it to be what? Boot 2 in. Then we can still see another structure. Don't forget, I'm here for what? For arcane now. I'm done with the words for the arcane. Now, if you see another structure like, let me say, something like this. What if we remove one of the carbon? What if we remove one of the carbon, put it here? Then what would this become? 1, 2, this one is 4. 1, 2, 3, 4. 1, 2, 3, then 4. If you check this, this is still, the carbon is 1, 2, 3, 4. Hydrogen is still 1, 2, 3, 4, 5, 6, 7, 8. It's still the same thing. But if you check this very well, this one is, the longest chain is this. And there is a methyl here. So we have this to be 2 methyl, what? Propane. 2 methyl propane. 2 methyl propane. But don't forget, we have a general formula for arcane. We have a general formula for arcane, but the general formula says when n is odd, you have it to be 2 raised to power n minus 2. But when n is even number, when it is even number, we have it to be 2 raised to power n minus 2 plus 1. Then if you check this very well, we can still produce with this structure. This structure still remain. We can have something like this. If you have 4 bonds, you know it is 4 bonds, you have something like this. 1, 2, 3, 4, 5, 6, 7, 8. Now if you check this very well, this is still C4, H8. But this one does not have the presence of the double bond. But the name of this, because it is a circular form, we call this cyclobutane. Cyclobutane. Now cyclobutane, we can still have another one. So if you have another one, you have it to be this. We check it very well. We can have it to be this. That is under this cycle. Each carbon, don't forget, must be tetrahedral. That is 4 bonds. Now if you check this very well, how many carbon is here? We have 1, 2, 3, 4. And how many hydrogen? 1, 2, 3, 4, 5, 6, 7, 8. The same thing. But this one is methyl cyclopropane. Then if you check this very well, the number of isomers here is 1, 2, 3, 4, 5. Then at the same time, if you follow the formula here, which says when the number of carbon is even number, then you use 2 raised to power n minus 2 plus 1. Oh yeah, now the number of carbon we have there is what? Is 4. So if you now substitute in the formula here, that will be 2 raised to power, what's that? And that's 4 minus 2 plus 1. Oh yeah, everybody, what is 4 minus 2? That's 2. 2 raised to power 2 is what? 4 plus 1, that's what? 5. Making the numbers of isomers to be equal to what? 5. But this rule and this formula holds only for the structural isomerism. Now let me add one to it. That is for arcanol. So whenever you are asked to find the isomers for arcanol, just use the formula. Don't forget that arcanol is the same thing as alcohol. Just use the formula that says 2 raised to power n minus 2. 2 raised to power n minus 2. They don't normally ask for the alkyne. But because of those that can ask me the question on alkyne, so let me just give you, for alkyne, when you have the number of n to be odd, just use the formula that says 2 raised to power n minus 2n. But when it is even, when n is even number, just use 2 raised to power n, then minus into bracket 2n minus 1. This is the formula. Now, with this formula, you are going to go with the what? With the number of isomers for those doing what? For those doing the CBT exam. Now, let us move to the another isomerism. Now, the second part of the isomerism we'll be looking at is the positional isomerism. Now, when you're talking about the positional isomerism is the type of isomerism in which the compounds undergo the compounds with the same molecular formula, but they have different position of the functional group. Different position of the functional group. Let us check. Now, the same molecular formula, but different position of the functional group. Let us see, for instance, if you have C5H, that's 10. This one is called pentene. This is called pentene. Then we check the pentene here. You can have this to be 5. If I have this to be this, without even completing the structure, we check this very well. We check this very well. This one is called. We check this very well. 1, 2, 3, 4, 5. That's pentene. But the position of the functional group is found at what? At the second carbon here. So it is called It is called pent2-ene. It is called pent2-ene. Then what if it is found here? 5. Now this one is called pentene. It is called pentene, or call it pent1-ene. It is called pentene, or call it pent1-ene. So this one, we call it, they are structural isomerism. They are positional isomerism. That is, we have this position of the functional group here to be on the second carbon, and this one to be on the what? On the first carbon. So we call it positional isomerism. Positional isomerism. So they are positional isomers of what? Of each other. They are positional isomers of each other. At the same time, we can have the positional isomerism in terms of alpha, beta, and gamma. In terms of alpha, beta, and gamma. Now, for instance, you can have something like this. You can have something like this. If you have OH here, and you have, let me say there's OH here, and you have a methyl here, CH3. Then if you check this very well, and you have something like this, you have OH here, and you have CH3 here. And at the same time, I'm using the same thing. You have it to be this. OH is here, and you have the CH3 here. Now, the alpha is the carbon that is next to the carbon of the functional group. The beta is the carbon that is next to the carbon of the alpha. And the gamma is the carbon next to the carbon of the what? Of the beta. So if I want to name this, I can say alpha methyl. Then what's the name? 1, 2, 3, 4, 5. That's pent. We call it what? Pentanol. Alpha methyl pentanol. Then with this, I can say beta methyl pentanol. Don't forget, the alkanol is found on the first carbon. So then I can call this a gamma methyl pentanol. And the positional isomerism can also be examined. So all these are differ. They are the same thing if you check. They are the same thing. The same number of carbon, the same number of what? Hydrogen. But they are differ in the position of the what? Of the ligands here. And at the same time, we can also have the position of isomerism in terms of octo. We can have in terms of meta, and we can in terms of what? Para. For instance, if you have something like this, if you have benzene structure, let's even use the phenol. If you have the phenol structure, don't forget that the phenol structure is gotten from what? From the addition of OH to the benzene structure. Then if you have something like this, you now have something like NH2 here, or you can have, let's even use chlorine. Let's use chlorine here. You have something like this. You have OH here. You still have, maybe let's put the chlorine here. You still have the structure here. We have the structure here, OH. Let's say you have the chlorine here. Now, when you check this structure very well, when we have this as a benzene structure, then they are differ in what? In the position of the what? Of this ligand, which is the what? Which is the chlorine. Now, what is now the name of this structure? If you check very well, they will have the same number of carbon, the same number of hydrogen, the same number of oxygen, but they are different. So if I want to name this, I will now say O-chlorophenol. This one is called O-chlorophenol, and this one is called M-chlorophenol. The difference is that this one is found at the carbon next to the what? To the functional group here. So this one that is found here is called what? Octo. This one that is found very close, the carbon next to the carbon of the octo is called metal. And the carbon next to the carbon of the what? Of the metal is called what? Para. So you can say this to be M-chlorophenol. M-chlorophenol. Don't forget, the structure of the benzene is circle, like is in circular form. Don't forget that they can change. This chloro here can also become here. That shows that this one as well is also next to the OH here. It can still be called what? Octo. This one is also next to the octo here, so it can still be called what? Metal. And the last one here can be called what? Para. So I believe I've been able to explain the positional isomerism. Now let us go to functional group isomerism. Now, what is the functional group isomerism? The functional group isomerism is the type of isomerism that occur in which you have different compounds with the same molecular formula but different functional group. Let us see. If you have something like C2H6O, C2H6O, you can examine this. It can give you CH3O, then CH3. And at the same time, you can have something like this, OH. If you check this very well, they have the same number of what? Of molecule. That is the same molecular formula, but different what? Different functional group. The functional group of this one is O. The functional group of this one is what? OH. So that's why we call it functional group isomerism. Don't forget, we have what we know as ROH. This one is eta family. Eta family. This is the functional group of eta. We have ROR to be what? To be eta family. We have ROH to be alkanol or alcohol family. ROH to be alcohol or alkanol family. Don't forget, we have many more functional groups like RCOOH. This one is what? Is alkanoic acid. Alkanoic acid functional group. We have RCOOR. This one is alkanoids. We call this alkanoids functional group or call it what? Ester family. We also have many more functional groups like RCHO. This one is alkana functional group. We also have RCOR. This one is alkanol family. Don't forget that alkana can also be known as aldehyde, and the alkanol can also be known as what? Ketones. So back to the functional group isomerism. They have the same number of carbon. The carbon here is 2, the hydrogen here is 6, the oxygen is 1. This one, the carbon is 2, the hydrogen is also 6, and the oxygen is what? 1. But this one is called dimethyl ether. Dimethyl ether. Can you see? Dimethyl. The methyl is 2, then ether family. That's what we call it, dimethyl ether. This one is known as what? Ethanol. Or we can call this dimethyl ether to be methoxymethane. We can name it straight up. You name it straight up like this. Methoxymethane. We call it dimethyl ether. So therefore, the methoxymethane and the ethanol, they are isomers of each other. They are isomers of each other. Let me cite another example. If you have C3H6O, C3H6O, see this one? You have C, O, and H like this. You have this, you have this, you have this. Now see, CH3. The carbon is 3, the hydrogen is what? Is 6, and the oxygen is 1. If you want to name this, we'll call this propanal. This one is propanal. And you also have this one, C. You can have this like this. Hydrogen, don't forget, each hydrogen must be tetrahedral. You have it like this. Now if you check it very well, this one is, the carbon is 3, the hydrogen is also what? 6, and the oxygen is 1. So we'll call this propan 2,1. So they are what? They are functional group isomers of each other. The same thing with this, dimethyl ether and ethanol. The same thing with propanal and propan 2,1. They are functional group isomers. So aside the functional group isomers, I believe this is the third one. And the fourth one, let us go to the stereoisomerism. Now we are talking about the stereoisomerism. The stereoisomerism is defined as the compound with the same molecular formula, the same structural formula, but different arrangement in the space. The same molecular formula, the same structural formula, but different arrangement in space. That is the stereoisomerism. Don't forget that I told you that stereoisomerism is differentiated or is divided into, we have the geometrical isomerism, and we have the what? The optical isomerism. The geometrical isomerism and the optical isomerism. Let me firstly define the geometrical isomerism. The geometrical isomerism, as the name implies, geometrical isomerism can also be known as cis-trans isomerism. The geometrical isomerism can also be known as cis-trans isomerism, and as well the optical as well can be divided into two. We have the rotation of the plane mirrors that we are using for the optics. So we have the one we call the level rotatory, and we have the retrorotatory. So if it is level rotatory is when the plane polarized light is, or the plane polarized mirror is rotated to the left. That is level rotatory. And the retrorotatory is when it is rotated to the what? To the right. That's the difference between the two. Now, let me talk about the geometrical isomerism. Now, the first one, it is divided into cis-trans. What did I mean by cis-trans? Now, it is cis when the ligands are found at the sides, but it is trans when the ligands are opposite each other. That is, they are opposite like this, they are looking at themselves. Now, let us see the cis structure. Now, this geometrical isomerism always have, they are peculiar to Akin family. They are peculiar to Akin family because that most especially the 18 structure, this is because of the rotations of the compound. And that is why it is peculiar to Akin family. Now let us talk about the Cs. Now see this one. If you add this, for instance, I will use A and B to denote, the ligand. So if the ligand is found, this one now, the ligand is found at what? At the top side. Then if you have the ligands like this, to be found at the what? At the below side. The ligand is found at the below side. Then all these are what? Are Cs. Even if they are found at the what? At the right side. At the right side like this, they are called what? They are still what? Cs. Even if it's found at the right side, this one is left. So if it is found, if the ligands are found at the what? At the right side, it is still what? Cis. This is cis isomers. Now what is trans? Trans is when they are found at what? At the diagonal. Don't forget that is they are found opposite each other. Can you see the ligands? They are found opposite. Or when you have it like this here, you have the carbon here, you have the other ligands. So when it is found opposite each other like this, either this or this, then we'll call it what? We'll call it trans isomerism. We'll call it trans isomerism. Now let me give you an instance. Now if you have something like this, CH3 here, you have this hydrogen, and you have another one to be CH3 here, you have CH3 here, you have hydrogen here. Now if you check this, the numbers of carbon here is 4, but the double bond is found at the what? At the middle, that is the second carbon. So I can call this cis but 2in. Cis but 2in. It is named as cis because the two ligands are found at the same side. But check this, they are found opposite each other. So if I want to name this, I will say trans but 2in. Trans but 2in. So therefore, this trans but 2in and cis but 2in, they are geometrical what? Isomers of each other. Let me give you more example. Now, what if this is replaced with another ligand? What if it is replaced with another ligand? Let's say, for instance, you have something like this. You have the chlorine. You have the chlorine here. You have the chlorine here. You have hydrogen. Now, if you check this compound very well, the chlorine here are still found at the what? At the what? At one side. They are found at the downside. So, because they are found at the same side, we call it what? Cis. So now have it to be cis. Don't forget that we have the chlorine first. So it will now be cis 1,2 dichloro what? 18. Dichloro 18. Cis 1,2 dichloroethene. So the chlorine are found at what? The first carbon and the second carbon. We have it to be 6,1,2-dichloroethene. Then the reason why it is called 1,2 is because we have the two found at what? At the first and what? At the second carbon. Now if you check this one now, this one we have a chlorine here, we have another chlorine here. So it is opposite. Though I don't want it to be like the other one we did. So let us put the ligands here, that is the chlorine is here, ligand is also here, the chlorine. So it is what? Opposite each other. So we can call this trans because they are opposite. So now says trans 1,2-dichloroethene. And the reason why it is ethene is because don't forget it is two carbon and it has the presence of what? Of the double bond. So this 6,1,2-dichloroethene and trans 1,2-dichloroethene, they are geometrical isomers of each other. And let us go to the optical, the optical isomerism. Now, what is optical isomerism? Now, in case of you that cannot see this very well, then check it very well. Check the example very well. Then let us go to the optical isomerism. Now, what is optical isomerism? Now, don't forget that I told you that the optical isomerism deals with a plane mirror. Now, we normally use the example of optical to be lactic acid. Now, lactic acid, for instance, because if you see the structure of the lactic acid, you have, let's say you have the chlorine here, you have OH, you have COOH, you have the CH3, and you have H. Now, the lactic acid undergo the optical isomerism because if you see it very well, this is the most common example. Now, why do we call it optical isomerism? Because it will be at the front of the what? Of the plane mirror. This thing is like placing yourself at the front of the plane mirror. Now, if you place yourself at the front of the mirror you use in your house, that is the dressing room, you observe that you see the front side of yourself ahead of the what? Of the back. So that means that the optical isomerism is surely saying that if you place this at the front of the plane mirror, the structure that we observe here, that is, it will show this before what? Before others. That means you can have something like this. Let me draw it like this. You can have something like this. This is what we mean as optical isomerism. Though in some textbook, you see them drawing the C as normal C. Yes, fine. Yes, fine. Because if you see this very well, so it's like you are saying another one like this. Let me give you another one. Let's say you have H3 here. You have C, H2 here. Don't mind this compound. Don't mind this compound. So if this also undergo the what? The optical isomerism, you can have it to be H3 will come first before the C, then before what? The CH2 there, then what? Then OH here, then we have what? We have H here. This is what we mean by optical isomerism. So don't forget, I told you, it's also divided into two, whereby we have the level rotatory and the dectro-rotatory. The level is when it's the plane polarized mirror is rotated to the what? To the left. And the dectro is when it is rotated to the what? To the right. And lastly, under that, don't forget, we have what we know as chain isomerism. Now, what is chain isomerism? Now, because of my time, I'll just use these three examples to explain the chain isomerism. If you have something like pentane, pentane is 5. Don't forget, pentane is 5. If you have this, it will be 5. Pentane. Now, on the norms, we'll call this normal pentane. Normal pentane. So this one is normal pentane. The same thing, they have the same number of carbon, the same number of hydrogen, but different way of their what? Of their arrangement. Now see, if you have something like this as well, the pentane, we see this. I can call this isopentane. I can call this what? Isopentane. You observe that this metal is found at the what? At the one carbon like this. So I can call this what? Isopentane. So it is found at the second carbon. It is found at the second carbon. So I can call this what? Isopentane. And we have what we know as neopentane. Neopentane. We have this. Neopentane is this. So they are different in the what? In the chain. They are different in the chain, the way they are being chained. So that's it. The way they are being chained is their what? Is their difference. If you check this and this, they have the same number of carbon, the same number of hydrogen, the same number of carbon and the same number of what? Of hydrogen. So this one is called neopentane. Now if you check this very well, in the next video, I'll be giving you the difference between the N, the normal. We'll call this N normal. Whenever you see N in the naming, we'll call this normal. We have what we know as iso. We have what we know as sec. We have what we know as start. We have what we know as neo. Yes. So from this, I will definitely explain all this in the next video. So before that, let me know, summarize or give me two differences in the comments. Give me two differences that you can see between each of these isomers. What did I mean by that? That is, tell me, or let me even say, let me give you this. Just give me two explanations from your side. Two explanations from your side on each of these isomerism I just explained. Thank you very much for today. I believe you've learned something. So please like, comment as well, and subscribe. Thank you very much. God bless you. I mean, God bless you.